So again, so just repetition. Dot product, you have two vectors, A and B.
Professor,
Yes?
we can see your screen, but I don't think we can see the actual slides that you opened up. Maybe that's just me, but I can only see the screen behind that, like the files and stuff.
Okay, so should be slides dot product. So anybody can see the slides?
No,
we can only see the
no.
files.
No, Professor.
So this is what I was afraid of, that we may have problems. Let's see how to do this. No, this will not work.
I think when you share your screen, you have to click your slides so that we can see them. Like
now, can you see it?
No.
Still no.
I think so. Like what they were recommending, someone who just spoke. You can like open up the slides and then stop sharing your screen, and then when you share it again, choose the slides to share. Maybe that will work.
Okay, let's see. Stop share. And now share screen again. Can you see now? Can you see the slides?
No, we cannot see the slides.
So something, it will not work today. You see, so again, I was doing this going through my ASU, and this doesn't work today. So you don't see anything.
We don't see anything, just a black screen.
So let me open this again. I am opening this one more time. Can you see now?
No.
Stop share. So I stop share and then share screen again. What about now?
We see
Yes,
it now.
we can see it now.
Yeah.
Yeah, no.
The dot product, yeah? It's written dot product.
Yeah.
Yes.
Oh, gee.
Yes.
So let's go. So you remember when you have two vectors, A with components A1, A2, A3, and B, B1, B2, B3, the dot product, you just multiply A1, B1 plus A2, B2 plus A3, B3. So easy definition, easy to compute. We mentioned some properties. So of course, A dot product with A is magnitude of A squared. We'll check it right away. You can compute dot product in any order. You can distribute dot product. So A, B plus C is AB plus AC. And if you have a scalar, you can put it in any place. So A alpha B is the same A, AB, and A alpha B. So you can put the scalar any place you want. So I don't know, so we probably still discussed this last time. So the theorem is that the dot product, so can you here is difficult to read, but look here. Dot product is magnitude of A, magnitude of B times cosine angle between those two vectors. So this is kind of the theorem. The dot product is. Now this theorem is mainly used to compute the angle between vectors. So if you have given two vectors and they ask you to compute what is the angle between those vectors, well, so you use this theorem and you compute cosine theta. So cosine theta is A dot B. We know how to do this, yeah? You multiply component by component and you divide this by magnitude of A, magnitude of B. So that's how you compute the angle between two vectors. So here is easy example. So you have two vectors, A and B, and you would like to compute the angle between them. So of course, cosine theta is AB over magnitude of A, magnitude of B. So theta is arc cosine, inverse cosine. And then you compute it. So certainly, what is the dot product? Well, 1 times 4 plus 2 times 0 plus 3 times minus 1. So the dot product is 1. Now magnitude of this one is square root 14, magnitude of this one is square root 17. So the angle between those vectors is arc cosine, inverse cosine of this number. If you use your calculator, this is 1.5 radians, or roughly speaking, 86 degrees. Okay, so this was done last time, but now probably this is now a new thing, I think. So what is dot product? And what are the applications? Well,
I have a quick question. What
yes,
does corollary mean?
excuse me,
What does corollary mean?
what it is.
Yeah. Corollary, the last slide.
Orthogonal.
Yeah, I think it's in slide 3. Corollary.
No, corollary means consequence. Something you can conclude from the, there's a theorem, and what you can conclude from the theorem, it's called corollary, consequence.
Okay, thank
It
you.
follows from theorem 1 that, something like that. So that's a corollary. Consequence. Something that follows from something. So now, of course, vectors are perpendicular if the angle between them is 90 degrees. So if this is the case, we call the vectors perpendicular or orthogonal. So vectors are called perpendicular or orthogonal if the angle between them is 90 degrees or pi over 2 radians. So again, if you have, you know, the scalar product is AB, magnitude of A, magnitude of B times cosine theta. If theta is pi over 2, cosine theta is 0, and the dot product is 0. So this means that the vectors are perpendicular orthogonal if and only if the dot product is equal to 0. So this is easy check. So it's easy to check if the vectors are perpendicular or orthogonal. You compute the dot product. If the dot product is 0, they are orthogonal to each other. If the dot product is not 0, they are not.
So orthogonal just means perpendicular?
Correct. That's synonym.
Okay.
Orthogonal and perpendicular, those are synonyms. Perpendicular or orthogonal, same thing.
Okay, thank you.
Okay, so here is the example. Determine whether the given vectors are perpendicular, parallel, or neither. Well, so let's see. A and B. Well, here you see that kind of this vector is proportional to this. Yeah, you see that vector A, you can get vector A if you compute minus 2b. Yeah, what is minus 2b? Minus 2b is 2 and minus 4. So A is equal to minus 2b. So those vectors are parallel. They point in the same direction. So they are parallel. Proportional. Again, so the proportional vectors are parallel.
Professor, I had a quick question.
Yes?
Reviewing the slides we've already went over, and when it comes to the direction that a vector is going in, is the only way you determine that just by looking at the components and their signs? Is that how you do that?
Yes, you just plot the vector kind of, and then you will see the direction. If you plot this in 2 dimensions, you see that this vector looks more or less kind of x coordinate is 2 and y coordinate is minus 4, so it goes like this. So kind of would be, if this is the 0, it would go this way. So just to see how the vector looks like, just plot it.
Okay, thank you.
Now another one, you have 2 vectors in 3 dimensions. Well, so let's compute the dot product. When you compute the dot product, well, easy algebra, you see kind of that 24 minus 9 minus 15, well, this is 0. So those 2 vectors are orthogonal or perpendicular, whatever you prefer. So again, easy to check if the vectors are perpendicular or not. You just compute the dot product. And again, another example. You can see that the dot product of those two vectors is not 0, it's 12. So the vectors are not orthogonal. You also see that this vector is not kind of proportional to this. Yeah, so kind of they are not proportional. So they are not perpendicular, they are not parallel as well. They are parallel if they're proportional, like here, yeah? But here you see that A is not equal to some constant times B. You can easily check it. So now there'll be important formulas on this slide. You'll have to use those formulas in your web work and so on. So here, look at the picture. You have two vectors, A and B, and the angle between them is theta. Now let's project this vector. Well, let's call this point P. Let's call the end of vector B by R, and let's project the point R to the vector A. Well, orthogonal projection. So there's a right angle here, and the point here you get when you do this projection. Let's call it S. So you have vectors A, B, and you have points P, R, and S. You can assume that the point P is at the origin of the coordinate system, so P may have coordinate 0, 0 if you want, but that's usually what we do. So now, this vector PS from here to here is called the projection of the vector B onto vector A. So that's a projection. So the vector which connects the point P and S, this red one here, is called the projection of this vector into the vector A. And notation for this, so PS is called projection, PROJ, yeah, just abbreviation from projection, of the vector B, and you put here subscript A. So this vector PS is denoted by this notation, projection of the vector B onto A. And the scalar projection, so this is vector projection. Vector projection is a vector, so PS. So this is a vector. This is a vector PS. So PS is equal projection of vector B onto A. And the scalar projection we call just the magnitude. Well, not really magnitude, the kind of the scalar projection is just the magnitude. Well, if you put PS to B, that's a cosine. So B times the magnitude of B times cosine, we call this the scalar projection, and we call this component of the vector B in the direction of A. That's the notation. Read component of B along A. Is the, well, length, not really length, signed length. So for example, in this case, this component is positive. If you would have angle going this way, this component could be negative. Yeah, the PS points in the same direction as A, so this component is positive in this case. So again, the scalar projection is positive if the angle is like on this picture, between 0 and pi over 2. If the angle is greater than pi over 2, when you project this, the projection will go in the opposite direction of the vector A. And then we say that the component is negative. So again, the scalar projection is positive when theta is between 0 and pi over 2, as on the picture, and negative if theta is between pi over 2 and pi. So of course, from the right triangle, this is the right triangle, so you see that the magnitude of the vector PS is magnitude of the vector B times cosine theta. Of course, cosine theta can be positive or negative. So that's why this thing can be positive or negative. The notation maybe is not perfect. Yeah, cosine can be positive or negative. Now, when you substitute, you remember cosine theta is dot product divided by magnitude. If you substitute this for cosine theta, you will see that the scalar projection will be dot product AB divided by the magnitude of A. So that's nice formula to memorize. Okay, so here you have in red and in a box with a component of the vector B along A is A dot B over A. So when they ask you to compute this, just use this formula. Of course, you could use this formula as well, but that's simpler usually. Now let's get the formula for the vector projection as well. So this vector here. Well, so to get this vector, you get the magnitude of this vector or sine magnitude, and you multiply this by the unit vector. Unit vector is A divided by the magnitude of A. So this vector projection is component and times this unit vector A over. So this is already a vector. A number times vector is a vector. Again, if you substitute this formula, you get this A, B over A over A, and you see that, again, you have a formula for the vector projection. So vector projection is dot product AB over A. You have A and A, so A squared, and times vector A. So those are easy, but you should kind of memorize those formula. When they ask you on the web work problem to compute the component, well, use this formula. When they ask you to compute the vector projection, use this formula. You can use this using brute force, going all the way to the definitions, of course. But then, in this case, you will be deriving those formula. So just, they are here, two important formulas. Again, put them on the piece of paper. Or when you take a test or something, you'll be asked, if you are asked to do this, just put those things on the piece of paper and use those. Those are the important formulas about the dot product.
Professor, quick question.
Yes.
If vector B were to be longer than vector A, then the projection would just be vector A, right?
No. It would be, well, it would be A times something. So you see, look, you this vector and make it bigger, like all the way here. The projection will go beyond vector A. What this would mean that the scalar projection would be, the magnitude of the scalar projection would be bigger than the magnitude of the vector A. No problem. Everything still works. Everything still works.
Okay.
No.
Thank
Yeah, vector B can be, yeah. So there's no restrictions on length. Again, draw the picture with bigger vector and you see that it's still, but of course you just project on the extension of the vector A. Just you put here the dotted line and make the projection, and maybe the projection would land here beyond the vector A, but that's okay. And again, of course, those formulas still apply. So again, keep in mind that those are two important formulas. Scalar projection, well, the formula is here, and vector projection, formula is here. So here, example, well, we'll be using those formulas, okay? So just you see, find scalar and vector projections of the vector B, so 1, 3, minus 1, onto the vector A with components 4, 2, 0. You can write this vector as 4i plus 2j, yeah? You can write this vector as I plus 3j minus k using those coordinate vectors. Canonical basis, if you want. Okay, so certainly to compute this, you see what we need. Well, we need to compute dot product, and we need to compute the magnitude of A. So certainly before we compute this and this, let's compute dot product, and let's compute the magnitude of the vector A. We don't need magnitude of B. So let's start with magnitude. So of course, magnitude of A is square root 4 square plus 2 square plus 0 square. Well, check it, that's square root from 20. You can simplify this as 20 is 5 times 4. Square root from 4 is 2, so this is 2 square root 5. So that's a magnitude of the vector A. And dot product. Well, dot product is 4 times 1 plus 3 times 2 plus 0 times minus 1. So it looks like it's 10. Yeah, so 4 times 1 plus 2 times 3 plus 0 times minus 1. So that dot product is 10. And now you're just using your formulas. So component of B along A, well, formula was A dot product B over magnitude of A. So you substitute 10 over 2 square root 5. So that's 5 over square root 5, which if you multiply by 5, square root 5, you get 5 square root 5 over 5, which is square root 5. So scalar projection is square root 5. When you do your homework and you get this answer, you can put this in a web work without simplification. If this answer is correct, the web work will accept it. And again, vector projection. Well, we have a formula. So the formula is A times B over magnitude of A squared times vector A. That's a formula. So you just substitute again. So AB is 10. Magnitude of A, well, if you take square, it will be 4 times 5. So that's 20. Yeah, so A squared, this square of this is 4 times 5, yeah? So which is 20. So 10 over 20. And vector A is 4 to 0. Well, so if you do algebra, that's 1, 2. So this is 2, 1, and 0. Or 2I plus J. Again, easy to use, but you have to know those formulas and just computations. So as I said, you will have a lot of problems to practice this on your web work. Any questions? Okay. Well, some application. Let's see, dot product application. So, how we can use such things. Suppose an object moves from point P, it's here, to point Q. So that's a displacement vector, PQ. Subject to a constant force. Well, this force, as you see, forms the angle theta. So there's an angle theta between displacement and F. Subject to a constant force F. Then the displacement vector is, well, so vector D, so let's call it vector D. PQ is vector D. The vector from here to here, let's call it vector capital D. So this point is moved, the distance this point moved is the magnitude of D. So of course the distance is the magnitude of this vector. So if you call this PQ displacement vector by D, the distance is magnitude of D. So now, the work done by this force, well, you see, so you know that if you take the force which makes the work is the projection of this vector F to this displacement. So kind of if you have this vector, so this vector is doing the work. And the work, of course, is force. You know from calculus 1 or from mechanics, if you took the work is a product of force, which is doing the work, and the force which is doing the work is the component of the vector F along this displacement, PQ. So component of the vector F along D. This displacement we call by D, which is of course equal to F times cosine theta. That's a scalar component. So the work is F times cosine theta, that's the projection, times the distance. That's the definition of work. Yeah, the work along the straight line is force times distance. The force which is doing the work is this component. So you have work is F cosine theta D. And of course you recognize this, that this is nothing else but the dot product. So the work is a dot product of force times displacement. So for example, if the work would be perpendicular to this displacement, well, the vectors would be orthogonal and the work would be zero, yeah? There would be no work because the projection of this thing to the displacement would be zero. So it's consistent. But anyway, this is kind of nice, easier to memorize than this. So to compute the work, you just take a dot product, F and displacement. So remember the formula. That's the formula for work. Works in any dimension, as a matter of fact. Works in 2 dimensions as here, works in 3 dimensions. So that's true in any dimension. Of course, the work is positive if this angle is between 0 and pi over 2. The work is negative if this angle is between, if the force would go this way. Well, the pictures are here. So remarks. If this theta is between 0 and pi over 2, well, we are going the same direction of displacement, the work is positive. If the force is like this, so theta is between pi over 2 and pi, then the scalar component is negative and the work is negative. And of course here, when the force is perpendicular to displacement, there's no work, there's no motion, yeah? You have here and kind of the point stays in the same place, there's no motion, the work is zero.
So professor, like the vector F is essentially just like the way a force is, for example, pulling an object, and then the vector D is representing like which direction the object is moving, and like the magnitude would be the distance it's moving.
Correct. Yeah, correct. Yeah. But again, you don't have to, if you use this formula, you don't have to talk about the distance, magnitudes, and so on, kind of just, which is the work. This is very convenient formula. The work is just dot product. If you have a displacement, if you have a force, well, to compute work done, you compute the product. And of course, you can get the conclusion. If the work is positive, this means that the force points in the same direction as the displacement. If the work is negative, the force, this component for points in the opposite direction. Yeah, so you see here, you make a projection and the projection points in the same direction as displacement, then work is positive. Here, the projection points in the opposite direction of the displacement, so the work is negative. And here, the work is zero because the projection of this vector F on the displacement is just zero. Yeah. The scalar projection is zero. The vector projection is zero as well. But that's, yeah. So I think there is one problem where kind of just to see, let's see. I think that's the last slide here. So find the work done by a force of 20 pounds. So we are using American system, yeah, 20 pounds. In SI system, the unit of forces is Newton, but here we are using American system. So the unit of force is pound, unit of displacement is foot. In SI system, of course, unit of displacement is meter. Newton meter. Here we are using American system, pound, foot. find the work done by a force of 20 pounds acting in the direction northwest, north 50, or here is the direction, in moving an object 4 feet due west. So we have a force which acts like this, that there's an angle 50 degrees with north direction. So of course, this means that there's 40 degrees here. If the object moves west, so object moves horizontal to the west. This is horizontal to the east, horizontal to the west. So that's assumption. We know that the object is moving west in horizontal motion. And the force is having, so if the force, this angle is 50, of course, the angle between force and displacement is 40 degrees. So of course you see that the force points in the same direction as D, so certainly you should get positive answer. So that's the first thing. When we compute the work, of course it will be positive because the force is pointing in the same direction as the movement. If the force would be like this, the work would be negative. Well, here kind of they are using this. Well, in this case, we need to use this formula. Okay, so here, of course, we need to use this formula because that's a dot product, but we don't have components of F, we don't have components of D. So, well, you could put here coordinate system and maybe figure this out. But in this case, it's easier to use this formula. So the work is magnitude of F, magnitude of D, because this is given directly. Magnitude of F is given, it's 20. We don't have coordinates. Of course, you could compute coordinates, yeah, would be 20 kind of cosine, sine, and so on kind of. But in this case, it's easier to use this formula. So FD cosine theta, and cosine theta is 40, you substitute and you get 61.28. The unit is foot-pound. You remember American system, the unit of work would be joule, but here we don't have a special name for this. The unit is foot-pound. That's a unit of work in American system. So here, in this example. But of course, there's another example when we have given components of the function f and components, as you will see, of the displacement. So in this other example, it will be easier to use this other formula, just dot product. Here, of course, dot product is not convenient because we don't have components of f and d in this particular example. So this other example is here. The force, so that's a different example. The force F, so 3I plus 4J plus 5K, displaces an object from 210 to 462. So of course the displacement is the vector 4 minus 2 is 2, 6 minus 1 is 5, and 2 minus 0 is 2. So displacement vector, of course, is 2, 5, 2. D, or displacement vector, if you call this A and B, the displacement, so okay, we call this A, we call this point B. So displacement vector, of course, is AB, which is 4 minus 2, 6 minus 1, and 2 minus 0. So if you do your algebra, that's 2, 5, 2. So we have a force, we have displacement. Of course, you could again try to use this formula. Yeah, that's fine too. But it's much easier here, just kind of, you compute just directly the work. The work is dot product. So F dot product D. So that's 3 times 2 plus 4 times 5 plus 5 times 2, and if you do your algebra, that's 36. Okay, So this is all about this slide. Now let me see again. It would be nice to go to Webwork today, but again, I cannot connect to my ASU as I told you at the beginning. There's something wrong with passwords. As they told me that some problems. After the class, maybe I will try to solve it. But now let me see if I will stop sharing and if I can say go to the next group of slides. So let me try to open new things. Let's see if this will work. Okay. Can you see it?
No problem.
No.
You cannot see it. Yeah, that's a problem. Yeah, so again, let me get rid of this. Get rid of this. So again, maybe let me open it first. Let me see if this will work like this. And then I will stop share. And now share screen. Now?
Yes.
Yes.
Okay.
Yes.
So that's great. Okay, so and there's another. So just we will not finish this kind of. So again, I would prefer to go to Webwork, but I cannot connect to Webwork today. So let's go and start new slides. So this is section 10.4, and it's called the cross product. Now, there's a definition here, which is kind of artificial somewhat. You have two vectors, A1, A2, A3, and B1, B2, B3. It should be B2 here. 2 is missing here, as you see. That's a misprint. Well, then the cross product. Well, cross product is again a vector. You remember, dot product of two vectors was a scalar. The cross product notation is A, this kind of cross here or X here, B, that's a vector. So the cross product of two vectors is again a vector. And here is a crazy formula. I, and here is A2B3 minus A3B2 and so on. Well, don't memorize this formula. It will be easier to memorize this if we use determinants. So that's the definition, very artificial definition, very difficult to memorize it and so on. But you can write this definition using determinants, and then this is much easier to memorize. So here is some introduction to determinants. When you have a determinant of order 2, so this is A, B, C, D, determinant of order 2 is AD. If you took algebra, you know this is AD minus BC. Determinant of a matrix is a scalar. And here we have determinant of order 3 can be defined in terms of second order determinants. So if you took linear algebra, you had this. So you knew how to compute the determinant of the matrix of 3 by 3 matrix. So first row is A1, A2, A3, B1, B2, B3 is second row, C1, C2, C3 is the third row. And what it is? Well, it's A1 times determinant you get if you get rid of this and this. So A1 times this determinant. Minus, so it's plus minus. A2, determinant you get if you cross this and this. So B1, B3, C1, C3. Again, this is linear algebra. And plus A3, determinant if you get if you cross this and this. If you cross this again, this, you get B1, B2, C1, C2. So that's how you should compute those things. So now, here is the example how to compute. And then, of course, determinants, and then you can get. But now, if you kind of compare this and this, you see that this is kind of determinant from the following matrix. This would be determinant here, this would be determinant here, and this would be determinant here. So you could write this as the determinant from 3 by 3 matrix, I, J, K, and then A1, A2, A3, B1, B2, B3. So that's the formula here. So, and that is, of course, much easier to memorize. So the cross product of two vectors, A1, A2, A3, B1, B2, B3, is equal to the determinant of this matrix. You have vectors I, J, K, those kind of coordinate vectors. And so you see, if you multiply this, you get this. And if you expand this, you will see that this will be equivalent. This will be equivalent to this thing. So again, don't memorize this formula. This is much easier to remember. So again, to compute the cross product of two vectors, you compute the 3 by 3 determinant. First row is coordinate vectors, I, J, K, and then second row are coordinates of A, last row are coordinates of B, and that's of course equal to I, determinant of A2, A3, B2, B3, minus J, determinant A1, A3, B1, B3, plus K, determinant A1, A2, B1, B2. Again, to compute this is some work, but this is just kind of mechanical, and of course, this is just very easy to remember. So that's, again, much easier than this. So forget about this definition. When they ask you about the cross product and how to compute it, use this one. Okay, maybe announcement. There will be no office hours today because I cannot connect to web work, and I will have to work with this kind of help desk to restore my access to my ASU. So no office hours today. Usually they are from 11:30 to 12:30. We will have them again Friday. I hope everything will be solved by this time. But now after this class, I will have to call the help desk and restore my access to my ASU. Okay, so here maybe for today, just last example. Let's compute it, yeah? So you have A, B, A has those coordinates, B has those coordinates, and they ask you to compute the cross product. Well, so use this formula here above. So the cross product is I, J, K, you put this always. Then you put coordinates of vector A, so -3, 2, 2. And then you put coordinates of vector B, 6, 3, 1. And then you expand, so that's I times determinant 2, 2, 3, 1, minus J, determinant -3, 2, 6, 1, and plus K, -3, 2, 6, 3, yeah? -3, 2, 6, 3. And then you continue. So that's I. This is 2 minus 6. That's the definition of determinant. Minus J, -3, -12, and plus K, -9, -12. If you do your algebra, you see that this is minus for I, plus 15J, -21K. Okay, so let's stop here. Any questions? So we just have definition of cross product. Once I get access to my ASU,